What we are going to do is to create our own material in COMSOL Multiphysics. The material we are going to create is alumina. We are going to insert the density functions, thermal conductivity, specific heat, dynamic viscosity, surface tension, modulus of elasticity, Poisson ratio, and the coefficient of thermal expansion. Opening COMSOL Multiphysics. So here you'll see two options: model wizard and a blank model. Ideally, you would normally create a model by clicking model wizard, but since we are not creating a model, we are only inserting material properties or creating a material, we are going to select blank model. In the model builder, we have the material section. Right click. The first option would be to add a material, which you would do if you were using the materials that are in the user-defined library or the COMSOL Multiphysics material library. But we are going to use a blank material option because we are creating our own material with its own unique material properties. Notice that in the settings window, there's a label section where you can change the material or the material 1 into the name of the material that you would want to create, which in our case is alumina. You'll also notice that there's a node for material properties, which you expand, which you can select from and add into the material content section. So let us see, we're going to create density, clicking the plus sign, add to material, dynamic viscosity. We are also going to have heat capacity at constant pressure, the Poisson ratio, the thermal conductivity, the Young's modulus. Let's see what else we're going to have. We have coefficient of thermal expansion. Right. Notice that this appears, the properties that you're adding are appearing in the material contents, and you can have suggestions of the names of that you're going to call these properties with in the name section. And then here, this is where we're going to insert the this name. We're going to call it here, and so that we can actually call it into the material as we're going to use it. Notice that the property units also are included here in the units section. Closing this node. Now let's go to material, basic. Notice that the settings window now changes. It now has output properties. It has model inputs. Model inputs. This node includes the features of your simulation in which the material properties will be dependent on. For example, if your material properties are dependent on absolute pressure, you select that, you would click and add that. If material properties are dependent on temperature like us, you click that. Now, if you scroll down, you see that it appears here under model inputs, meaning that if you type T, the simulation or the COMSOL Multiphysics programming will recognize this argument. Closing this node. On the output properties, this is where your material properties are. You can still add different properties if you had not added them originally, like we did at the beginning of the demonstration. Now we're coming to the basic node. We're going to right click. Here on the functions, you see there's an option for adding an analytic function. Ideally, adding an analytic function is advisable when your material property is a continuous function, meaning that it doesn't have regions where that equation is not applicable, regions of temperature. And then your interpolation section or option, you would use that when you have a table of properties, meaning that you have a table of temperature versus the values of a property that you're going to insert, meaning that you're extracting values or the plot of the material property from a table of data. Then the piecewise function, this is when our temperature it has boundaries in which our material property equation is applicable in. Now, we're going to use mostly the piecewise function. Why is that? If we go here, for example, I'm going to scroll up. You'll notice, let's look at viscosity, dynamic viscosity. It has three equations: 0.1, which is a constant value, applicable only in temperatures between 293 Kelvin up to 2250 Kelvin. And then you have this equation here, which almost like it's an Arrhenius plot, which is only applicable at 2250 and 2300. And then 0.0001 is applicable at temperatures outside that up until 10,000. So this is a piecewise function. And this thermal conductivity is also a piecewise function. Also, the density is a piecewise function. Most of these properties are going to be piecewise function. So we're going to start with density, piecewise function. I'm going to resize this window so that we can see where we are as we create the model. Now, piecewise function, changing the label to density, and then the function name, rho. Under the definition section, argument, that is what our material property is dependent on, temperature. Extrapolation, this is when the software has to estimate the material property values that are outside the given equation. So in these options, you tell the software what it can do if your equations have a limited boundary, for example, as here is described here in this piecewise function. You could say it must keep the last value constant in the curve, or it must do nothing, or use the nearest function, or give it a specific value, or it must use a periodic function. So in this case, we're going to select constant. To not complicate matters, I'm not going to explain the no smoothing. Let's leave it as is. Right, and then the intervals section, we are now going to insert these conditions here of density: 293, 2250. function, that's the equation here, which is minus 0,125 multiplied by t plus 4031.3. Let's see if this equation is plottable. In the graphics window, you can see that density is decreasing with an increase in temperature. Inserting the next function, which is applicable at 2250 to 3500, negative 0,8 multiplied by t plus 5050, plotting, right? Something that is very important to note here is that in these intervals, it is important to insert the value here in the end section. It must be equal to the next value here on the start section, whereby you are applying the second equation. If it is not, this is what might happen. Let's just change that number and try to plot. Do you see that? Intervals must be contiguous or continuous. So, changing it back. Right. Now we're going to go down to the units node. Argument is temperature. Sometimes the temperature is in degrees Celsius, Kelvin, Fahrenheit. So you need to insert that. And then hours is in Kelvin. So we're going to change this argument into Kelvin, and our function is in kilograms per meter cubed. And plot. Our next function is thermal conductivity. But before we do that, let me expand this node. Clicking alumina. What we are supposed to do with every property that we create, we must write it here so that the software will be able to recognize it and use it in the computation. So our property name, the function name, not the label. So you insert the function name, which is rho. Let me copy that, paste it. Right. So here is our function value or name. If I click basic, what I'm supposed to do is this. That is how we're supposed to write the function. You say rho, open bracket, and then you write the argument here, which is temperature, and close bracket, so that it knows that this is an equation that is dependent on a certain model input. Right. Now, next function is thermal conductivity. Which is also a piecewise function. Let me just copy this here. Okay, argument t. right? So it's saying unexpected unit of input, meaning that the units that we have currently for this property are not what the software recognizes. It's supposed to be watt per meter Kelvin. Click here, scroll down, means you have to insert these units because you did not insert them before. Right. Now it's good. Okay. Next property is specific heat. We are going to skip this for now. I'm going to come back to it. Let's move to dynamic viscosity. Right. It's saying syntax error in expression. So it's evidence that one, it doesn't know there's a problem with this bracket here. So there should be open bracket, close bracket. So that means there should be another bracket here at the end that is closed. Now it's saying undefined variable, R. So COMSOL Multiphysics calls R in a different way. It doesn't just say R. So it says R underscore const. Alright, and then plot. It will plot it because it knows what it is. Let's see what it looks like. Right, so let me change R into a value, which is 8,314. Plot. Okay. Then our next equation, surface tension Next function, the modulus of elasticity. Poisson ratio. What is this called? The units here. Nu, okay. I'm trying to avoid writing V because V is something else if you're using fluid flow. So So this is a dimensionless property, so you can leave it like this and write 1. Then we have coefficient of thermal expansion. What is it called here? Alpha, okay? Alpha is written alpha here on the variable. So we can write alpha T, which let's starts at 2190 up to 2500. Okay, 1e negative 6 multiplied by negative right. We change something here on dynamic viscosity. I do not remember myself writing this unit here. Okay. So let's maximize this for now. Now let's go back here and call these properties. So dynamic viscosity is nu T, and this is, call this Y, I should be calling this E. This now we are left with the heat capacity at constant pressure. Saving this as amino material properties demo 1. So we have here, so we're going to create this one, heat capacity. I left it for last because it looks like a very long equation. It is a continuous function, so we are going to use an analytic function. So what happens here is that we have heat capacity dependent on temperature, which equals the constant heat capacity plus, it's just a function or coefficient for which account for the energy required to induce melting, latent heat of melting, and there's the function right here, and then plus the ratio of the latent heat of melting divided by temperature of melting multiplied by this H with a hyphen is called a Heaviside function. Let me just write it here, zooming in. Side function. So you can simply do this. If we go to the internet here, just type Heaviside function COMSOL. You'll see a lot of links, but what is important is that this is how you write this function, or this way. So what we're going to use is this second one, FLC2HS, because that's the way it's called up in COMSOL. This Heaviside function allows for a step in an equation, meaning that if there is phase change, it will show us there, and then you'll see a spike in the plot. Then it is a function of a change in the surface temperature and the temperature differential. And then you account for latent heat of vaporization as well. It's a similar representation, and the only difference is you are only including now the vaporization properties like temperature of vaporization and the latent heat of vaporization. So these coefficients have their own equation which account for the ratio of the temperature change and divided by this here times the square root of pi. And then what I did was to insert the melting temperature and then temperature differential, and then the same thing applies for the vaporization coefficient there, just the temperature change there, which is 30, and then we have the vaporization temperature, and then I'm going to press enter here, it's confusing, and the total equation will look like this. It's a very long equation, and then we also include now Remember, we multiply with the latent heat of melting. There it is here. And there's the heaviside function there. And then there is a latent heat of vaporization there. So basically that's the long equation that we're going to insert. But since I've done the job to retype this the way I would insert it in COMSOL Multiphysics, basically this is how I would insert it with all these features there. So I'm just going to copy and paste this. See if that works. Let me insert this continuous function. So it's not a piecewise function. So I'm going to use analytic. And I'm going to say expression there. I already copied it, paste. Okay. And then here, let's say, what are they calling it here? They're calling it heat capacity at constant pressure. So we call it heat capacity. Calling it CP argument T. And then it's not a periodic function, but with the units for the argument K, and this is joules per kilogram Kelvin. So let's start at 293. Insert any maximum value here, let's say 10,000. It will continue. If we plot this, now let's view this. So without the heaviside function, we're not going to be able to see this spike here and observe a typical effects of phase change and accounted for it in the equation. So the heaviside function, let's expand this. It's a very long equation here. The what is that? FLC. That's it allows for us to actually demonstrate this here, phase change in the material as a function of temperature. Okay, so going back to here, heat capacity CPT. Right, now we are going to save again. So we have alumina as a material. So now what is left is to say save this material in the user-defined library. So I'm going to just name it a little bit, and could have already created this, let's say alumina 4, let's say alumina demo, right? So you can call this material any material that you'd like. Let's say you're creating any different material. You insert its own unique properties. Okay, let us save this. Right click on the name of the material. You'll see the user-defined property group. Add to user-defined library. So that is what we want to do. Click add to user-defined library. If you wanted to see this, right click on material and say add material. And at the bottom there is user-defined library. There is alumina demo there. If I was to delete this, just for the sake of demonstration, and I click this and I double click, there's our material coming back. So we've already saved this material properly. Alright, that brings the end of our demonstration.